Math GPT. Today we're going to explore an intriguing theoretical perspective in physics, a unified frequency framework for understanding electromagnetic phenomena and how it might relate to fundamental concepts like mass, energy, and physical forces. Let's start with something familiar: the electromagnetic spectrum. Electromagnetic waves are oscillations of electric and magnetic fields that travel through space. They're characterized by their frequency, which is the number of oscillations per second measured in hertz. What we call the electromagnetic spectrum is actually a continuous range of these waves with different frequencies. At the low end, we have radio waves with frequencies around thousands of hertz. In the middle, we have visible light with frequencies around 400 trillion to 700 trillion hertz. And at the high end, we have gamma rays with frequencies in the quintillions of hertz or higher. But here's a key insight. Humans can only directly perceive a tiny slice of this spectrum, the visible light portion. Everything else requires special instruments to detect. This limited perception might be keeping us from seeing a more unified picture of reality. The framework we're exploring proposes a fundamental equation that relates frequencies to force. This equation, which we might call the unified frequency equation, takes the form E equals phi times psi divided by k times r squared. Let's break down what each component might represent. E represents a force or pressure measured in newtons. Phi represents a primary frequency or source intensity. Psi represents a modulating frequency or factor. K is related to the impedance or coupling strength of the medium. R squared is the distance squared, giving us an inverse square relationship. An interesting aspect of this equation is the inverse square term, 1 over r squared. This matches well with how we know fundamental forces behave in nature. The electromagnetic force between charges follows an inverse square law. Similarly, the gravitational force also follows an inverse square relationship. Most intriguingly, if you plug in the right values for phi, psi, and k, you get a force of approximately 9.8 newtons for a 1 kilogram mass, exactly matching Earth's gravitational acceleration. This suggests a possible connection between electromagnetism and gravity. In this framework, mass itself could be viewed not as a fundamental stuff, but as localized self-sustaining patterns of electromagnetic waves or oscillations. Think of particles as standing waves of energy, similar to how we see standing waves form on a string when we pluck it. These standing waves represent stored energy, which is what we measure as mass. This gives us a new perspective on Einstein's famous equation, E equals mc squared. Here, E represents the energy of these localized electromagnetic waves, and c squared is the conversion factor between energy and mass. This viewpoint might even help address the mass gap problem in physics, the question of why particles have the specific masses they do, and why there are no particles with masses between 0 and certain minimum values. An important consideration in this framework is how limited our perception of the electromagnetic spectrum really is. What we can actively detect is just a tiny fraction of all possible frequencies. This might explain phenomena like wave-particle duality in quantum mechanics, where tiny particles can appear to behave as either waves or particles depending on how we observe them. From this perspective, particles and waves aren't distinct entities, but different manifestations of the same underlying electromagnetic reality, observed through our limited spectral window. This limited view might also be relevant to the mysteries of dark matter and dark energy, which don't interact with the electromagnetic force in ways we can directly measure. They might exist in hidden sectors or interact via dark photons that operate outside our observable electromagnetic window.